Let's develop the derivatives of sine x and cosine x using the definition of the derivative and some trig identities. The derivative of sine x will take as the limit as h approaches 0 of f of x plus h, which is sine of x plus h, minus f of x, which is the function sine x, all over h. And here we will apply the addition identity for sine. We can rewrite that as limit as h approaches 0 using the formula above, sine of the first term x, cosine of the second term h, sine keeps the addition sign, cosine of the first term x, sine of the second term h. Checking that that is the correct formula as shown. Don't forget to subtract the sine x term, and we'll write this all over h. Next, we will reshuffle some terms. Limit as h approaches 0. Let's write the two terms with the sine x right next to each other. Sine x cosine h minus sine x. We're going to regroup them in a moment, and let's separate them because the limit of the sum is the sum of the two limits. I want to evaluate the second limit here separately. Cosine x sine h over h. Now for the first limit. In the numerator, each term has a sine x. We're going to factor out that sine x. In fact, we're going to write it out in front of the limit. We can do that because sine x is treated as a constant as h is approaching 0, leaving us in this first limit with cosine h minus 1 over h. Similarly, in the right limit, cosine x is treated as constant, so we can factor that out in front of the limit as h is approaching 0 of sine h over h. Now we need to take a close look at each of these two limits. These two limits appear very often in calculus. I recommend getting very familiar with them. I'm going to call this first limit y1 for our graphing utility, this second limit y2, and we're going to see where these two limits are headed in a moment. So let's take a look at where the y1 and the y2 are going. I rewrote that last step again. Looking at the first graph on the top, there's our y1. As h is approaching 0, we're reading that on the graph as x values are going to 0. And it looks like that limit is approaching 0. So I'm going to substitute 0 in place of that y1, representing the limit where that limit was headed to 0. y2, the graph on the bottom, as h is approaching 0, looks like our x values are going to 0. That's how we'll read that. And that limit is approaching 1. So the limit for y2 is approaching 1. Putting it all together gives us sine x times 0, which cancels cosine x times 1, which equals cosine x. Hence we've established that the derivative with respect to x of sine x is equal to cosine x. And now we'll take a look at the derivative of cosine x on the next page. And to speed things up, I started the process out for us. Here's the definition of the derivative for cosine x. So take a look at the sum identity for cosine, how it keeps additional sign and it turns that addition sign to a negative sign. So there's some extra negative terms. On the last step, we reshuffle the terms to each have a cosine x term in them for the first limit. So similarly, let's factor out the cosine x because cosine x is constant. Limit as h approaches 0, leaving us in the first limit with cosine h minus 1 over h. This one has a subtraction sign. The limit of the difference is the difference of the limits. And at the same time, we can factor out the sine x in front of the limit as h is approaching 0. Sine x will be constant as we look at the limit of sine h over h. Those two limits are the same as before. There's our y1 and our y2. Our y1 was headed to 0. Our y2 was headed to 1. So this turned into cosine x multiplied by 0 minus sine x multiplied by 1, which gives us negative sine x. Hence the derivative of cosine x equals negative sine x.